Hi everyone, so today we are going to learn differential equations for today's class. So first of all, let me ask you the question, what is a differential equation? Something you have learned in calculus, maybe, and let's review the concept of differential equations. Okay. Okay, so the definition for differential equation is that if a function describe or include one or more variables which are derivatives. Of the function, then we call the function a derivative equation. Okay, so in terms of the derivative, we know we can do first derivative, we can do second derivative or third derivative or any other higher order of derivative, and then the order of derivative determines the order of this differential equation. The order of the derivative is the order of the differential equation. Okay, let me give you one example. If you have dy cubed to dx cubed plus y squared equals to 2. What is the order of this differential equation? Because the derivative is third order, so we say this is a third order derivative. To solve this differential equation, let's start from the simple case by looking at a first order derivative. Let's see how to solve the problem. Okay, let me give you one example, a generic form. So if I have dy over dx plus a function q, which depends on x, times y, the function itself, which will equals to fx, another function depend on x. How can we solve this first order differential equation? So we see the differential equation we want to solve for y. It's very intuitive to say, oh, we want to do some integral. But to do integral, we want to separate the variable y and x now. And the fx seems really complicated the situation. So what people do is to first of all think about the reduced form of the function by setting fx equals to 0. Then we have dy over dx plus qx times y equals to 0. Okay, so now the new equation seems to be more solvable. And the trick we are using today for this type of question is separation of variables. Okay, so we want to separate x from y. Then we can put all the relevant terms regarding y to the left-hand side of the equation and all the terms regarding x to the other side of the equation. If we do so, what we can get? So first of all, dy over dx equals to negative qx times y. We can move this term to the right-hand side of the equation. Now I want to move the y to the left-hand side of the equation and x to the right-hand side of the equation, which will give me dy over y equals to minus qx dx. Now everything I have on the left-hand side is related to y, and everything I have on the right-hand side is related to x. And it's natural to think, okay, I can do the integration on both sides. So now if you forget how to do integral, you can go back to phase 2 and review the relevant concepts. So on the left-hand side, if we do the integral, we got log x. Okay, so how about the other side? Because we do not know the explicit form of the qx yet, we just leave it as it is. Negative integral qx dx. Because this is an indefinite integral, do not forget to include the constant c for the results. Okay, so now this seems to be straightforward to solve for the solution for this reduced form of the first order equation. Okay, and furthermore, it's y here on the left-hand side instead of x. Let me erase that. Okay, so it's log y equals to the integral of a function of x. Now if we further take the exponential on both sides, if I take exponential on log y and exponential on the right-hand side, exponential to the minus the integral qx dx plus c, we can actually find out y equals to exponential negative integral qx dx plus c. This is one solution for y for this first order differential equation. Okay, and now let's go back to look at the non-reduced form of the original function. How are we going to solve the non-reduced form of the function? And actually we are inspired by the solution of the reduced form of the function. So the strategy people use here is to introduce a factor called integration factor. So what is an integration factor? Let me use u, the letter u, to represent the integrated factor. So integrated factor looks very identical to the generic form of the solution of the reduced function. So it's actually defined as exponential integral of qx dx plus c. Okay, so why this integration factor matters and how are we going to apply the integration factor? And let's see. First of all, if you take the derivative of the product of u times y, what are we going to get? So you can pause the video for a minute and try to work on your own and then come back to check with my answer. Okay, so using the rule for determining the total differentiation of the product of two variables, we got the uy over dx equals to, first of all, I keep u the same, I take derivative of y versus x, then I keep y the same, and I can take the derivative of u over dx. Okay, and then in this case, we can actually see, because the u is defined as the exponential of the integral of qx dx dc, you can further plug that in, but that's not the concern at this point. We can leave as it is right now. So let's see why this integration factor actually matters. Okay, so let's go back to the non-reduced form of the first order differential equation. Let's multiply the integration factor to every single term in that equation. Let's see what we have. So let me multiply the u to all the terms in the equation. So I multiply u times dy dx. Okay, and then for the second term, I multiply u to qx Qx and y. On the other side of the reaction, I multiply u to fx. Okay, so let's try to see what's going on with this term. Okay, so now if we try to compare the total differentiation of the du times y and the left-hand side of the equation, let's see what we can find. Okay, so let's try to explicitly write out the results of both terms. Okay, so if we have the uy times dx, which give me u times dy dx, and the second term would be y times du dx. Now going back to see the definition of u, which is the exponential of an integral to the power of the integral. And if we plug that into the equation, what we can find is we actually got the u times dy dx, and for the second term, we actually got the y times qx times u. Okay, so if we plug in the assumption, the integration factor into the equation, this is what we got. Okay, so now what you can find here, if we try to compare the result of the total differentiation of the u times y and the left-hand side of the equation after we multiply u, what do you find out? They are the same, right? And in other words, the left-hand side of the equation after multiplying the integration factor is actually equals to the uy over the x. Why this is important? Actually, we can see if we have the integral derivative of the u times y over dx on the left-hand side and u times fx on the other hand side, it actually make the integration so much easier. If we go ahead and do the integration on both sides of the equation, what do we get after the integral is u times y equals to the integral of u times fx plus c. Because this is an indefinite integral, do not forget to include the constant c. Sometimes this c is usually ignored or forgotten, so remember to include the c here. Now you can see we got some results regarding the function y, and if we divide both sides by the u, we can get the generic solution for the function y. Okay, so we can do 1 over u, and on the right hand side we got the integral u times fx plus c. Okay, so far this is the generic solution or one solution for the y in the first order differential equation, the non-reduced form, while this one is the solution for the reduced form. This one is non-reduced. With the general format of the solution, we can go ahead and try to solve the specific real problems. Okay, so let's see several questions regarding kinetics. Okay. So how the differential equations are going to help us to solve problem in kinetics in physical chemistry. So the first question that we're going to work on is the rate of a chemical reaction is proportional to the concentration of the reactant. At time t. Okay, so these are all the information I know. The question I'm trying to find out is, please find the integrated rate equation describing this process. Okay, so now you can pause the video for 5 to 10 minutes. Try to work this problem out based on the method we are trying to use to solve the reduced or non-reduced first order differential equation, and come back to see how I'm going to help you solve out this problem. Okay, so hopefully you get some attempts going on for the solution of this problem. Okay, so to analyze the problem, we need some chemistry knowledge and some math tool to solve it together. So first of all, how to translate the language, the information we have, into a chemistry and mathematical language. I know the rate of the chemical reaction, so you can write it out. The rate of the chemical reaction, usually we use R or rate directly, is proportional to the concentration of the reactant. How to represent the rate of a chemical reaction? So try to review the portion you learned in General Chemistry 1 or Chem 115. Because the chemical we are talking about here is a reactant, so whenever you have a reactant in a chemical reaction, we are consuming the reactant. So the concentration of the reactant, we can call it concentration A, is actually decreasing. That's why we put a negative sign here. And what is the rate of the change of the reactant? Well, you can use the differential dA. And how does the concentration change over unit time? We divide it by dt. So the negative dA over dt, that's my turn to describe the rate of this chemical reaction. That's the first part of the information I can utilize. And then what's the rate is determined? Now let's check it out. It's actually proportional to the concentration of the reactant at any time t. Okay, I know this is my rate. It's proportional. Okay, so I can set a constant represents the proportionality k. It's proportional to what? Proportional to the concentration of the reactant A at any given time. So far I have set up the equation I'm trying to solve based on all the equation I want to get. So in order to find the integrated rate equation of this process, basically I'm trying to find out what is the expression of my function A, which is a function of t. This is what I'm trying to solve. Now looking at the feature of this function, we got the differential of the function, and it's a first order. And if we compare to the form of the reduced one and the non-reduced one, actually we can rewrite the equation that we are trying to solve. So the one that we are trying to solve is the first differential of A over time t, dA over dt, plus k times A equals to 0. Okay, so at this point, if you are not comfortable with correlating which is the variable, which is not the variable, you can try to write it out on your scratch paper by comparing to that. So the A here is equivalent to the Y in the generic form of the function, and my t is the variable which is equivalent to the x in this function. Okay, and the qx in this specific case is simply my k, which is a constant, okay? And my fx is actually 0 in this specific case. So we can just go ahead and plug in the generic form of the solution. So you can actually find out the solution for y, which is a here, should be equals to exponential negative, and in the integral term, the qx equals to k, and then to integral with dx, but you need to multiply by c here, okay? So we can further solve out this integral. So if you have the integral of k dx, which simply give me kx and plus some constant c here, okay? To further find out the equation for the integrated rate equation, this is not the end. We need to consider the initial condition that we have by plugging the values of y at time t. Okay, so after we get the solution for that one, we also need to, okay, so let me make one correction here. So instead of x, we should plug in t for the variable. Okay, one more condition that we know is at time 0, the concentration of A is the initial concentration. Usually we use A naught to represent it. If you plug this value into the equation, and the final results we can get for the concentration of A is equals to A naught times exponential negative kt. Okay, so you can compare what I work out with your solution. If you got some problem setting up the problem, we can actually review the general chemistry or physical chemistry. If you have some trouble plugging the generic solution into the equation, you can try to use the strategy of finding the correspondence. If you forget to plug in the initial condition to find out the C value in the generic form, you can add this up. Okay, so these are the important components for this question about the reduced form of first order differential equation. And to get more chemistry insights from this problem, if you plot out the concentration of A versus time, okay, so you can actually find out you have some initial concentration at A naught, and over time t, you got the exponential decay of the concentration for the reactant. It drops really quickly. Okay, after this, let's work out a second problem. In the second problem, I have a chemical reaction which involves two steps, changing from A to B, and then B converts to C. For these two steps, the rate constant is K1 and K2, respectively. Now I tell you that the concentration of B follow the following relation. So B is sometimes called intermediate. So you have the reactant A, and A is converted to some intermediate species, and but B is not going to stay there. It will transform into C, which is our product in the end. But if we want to study the intermediate, the concentration of B actually follows this relationship. So the concentration or the rate of concentration of B change, dB over dt, equals to K1 times A naught, which is the initial concentration of A, times an exponential decay term, exponential negative K1t, and a second term is minus K2 times the concentration of B. Okay, so this is what we know. Something we try to find out is find the concentration integrated rate equation. Describing the concentration of B with time as a function of time. Okay, this is our target. Now again, going back to look at the information we have, we got the function of B, which is the first order derivative, and the B also shows up on the other side of the equation. I would first of all reorganize the equation to the form that we are familiar with to find out the generic solution. So let me do that. So if we move all the terms involving B to the left-hand side, we got dB dt plus K2 times B, and all the time or the t dependent term on the right hand side of the solution, which is K1 times A naught times E negative K1t. Okay, again, if you are not comfortable seeing this equation with a new set of variable, you can actually find out the correspondence. So the B here is actually the same as the Y in the generic form of the function, and then the Q and my B2, which is a constant, is the same as Qx, and time t here is equivalent to the x in the original function. So if you are not so comfortable seeing a new set of variable, this is the way to go. Okay, also we got my fx equals to K1 times A naught times exponential negative K1t. This one is equivalent to fx. Okay, so now we have the non-reduced form of the first order differential equation, and we know the trick is to utilize the integration factor u. Okay, so for this specific case, we first of all need to find out what is the u in this case, because the q can change in different reaction, in different equation. So we got the exponential integral of qx dx. That will be my integration term. And since my qx is K2, I just plug that in. I'm doing integral of K2 dx, okay? So exponential, the exponent term is a simple integral that you know how to do. So which will give me K2x. That's my integration factor I'm ready to use for the u. Okay, so the next step, you can follow the same strategy. We can multiply the integration factor on both sides of the equation. If we do that, we are going to have e to the K2. It should be t here. It's the new variable, K2 times t, e to the K2 t times my function dB over dt plus, and the second term multiplied by the integration factor e to the K2t times K2 times b. On the right-hand side of the solution equation, I multiply the same integration factor e to the K2t times K1 times A naught times exponential to the negative K1 t. Okay, so what we can find out is this guy is simply the d of u times y. So what is my u? My u is e to the k2 times t. What is my y? My y is b that I'm trying to solve here over dt, which should be equals to the u e to the k2t times my fx. You just write it down. The same thing. Negative k1t. Okay. So after we get the equation, as usual, we do the integral on both sides. Okay, so now you can spend a few minutes try to work out the integral and reorganize the whole equation. Let's see what we find out, and we can compare our results in a few minutes when you come back. Okay, so let's come back and look at the problem together. Okay, so if we move the dt to the other side of the equation, we have the integration of a differential term, e to the k2t times b. Okay, and on the other side of the equation, we got the integral of e times k2t times k1 a naught times exponential negative 2k1t. The whole term are going to be integrated with respect to variable t. Okay, so if we proceed and do the integral, we got e times k2t times b on the left-hand side of the equation. Notice that the differential and the integral, they cancel with each other. And on the other side of the equation, the integral we are trying to solve is for a exponential function. So first of all, the k1 times a naught, which is a constant, can be put in front of the integral term. And how to do the integration of an exponential? So if we do the integral of an exponential, we still get the exponential function, which is k2 minus k1 times t, but do not forget to divide the term by k2 minus k1. Okay, so this is something we learned in phase 2 about how to solve integral. Since this is an indefinite integral, do not forget about the constant c for that. Okay, so our final goal is to solve for b, and we can divide both sides by e to the k2 times t. If we divide both sides by ek2t and ek2t, we can get the expression for b in terms of t. So now what we get is ek2t, and on the denominator we have k1 times a naught. So the k2 and minus k1 can be pulled to the denominator, and on the top we have exponential k2 minus k1 times t, and plus constant c over exponential k2 over t. Okay, are we done here for the expression of a concentration of B in terms of T? No. Like what we did before, we need to consider the initial concentration of the species B at time 0, which can help us to solve the constant C. Okay, so follow that strategy. If we plug in T equals to 0 at the time T, B is the intermediate species which has not been formed yet. So the concentration of B should be equals to 0. If you plug in the T equals to 0 and the B equal to 0 into this equation, you should be able to solve for C, and you can work on this by yourself. I want to give you the final answer so you can actually check it out. So the C we find out should be equal to K1 times A naught over K1 minus K2. And the final expression for concentration of B equals to K1 times A naught over K2 minus K1 times the exponential minus K1T minus e to the negative K2T. Okay, so here's the final answer that you should achieve after you work all this out. To give you the chemical insight towards the plot of the concentration of B versus time t. Okay, so we know that at the beginning, there's no B. If you follow the graph, you solve it. So first of all, you will find out the concentration of B should increase. At a certain point, it will reach a maximum, but afterwards, it's going to decrease because the B are used to generate C, which consume B in that sense. So this is the trend of the concentration of B along the progression of the chemical reaction if you use the expression to plot that. Okay, so far we talked about two scenarios about first order of a differential equation, the reduced form and the non-reduced form. And we'll look at the two examples about a kinetics question in physical chemistry. Okay, so now let's try to work out a example together. Okay, practice time. I will give you two questions to solve, and you can work on your own. So the first one is x times dy dx plus 2y equals to x squared. How to find out y for this differential equation? The second question we are trying to solve is x times dy dx minus y equals to x. In addition, I know that when x equals to 1, y equals to 3. Okay, so now spend 10 to 15 minutes to work out this problem, and we are coming back to see the solution together. Okay, you can pause the video to do that. Okay, so now you have solved the problem, and let's check out the solution together. So for the first one, whenever I solve a first order differential equation, I want to reorganize and make some changes to the reaction to follow the generic form that I'm familiar with. So I can plug in the integration factor and I can plug in the generic solution for that. So to achieve this goal, I will divide every term in the equation by x, which will give me 2 over x times y and x. So this is the equation I get. If you are not familiar with the formatting of the first order differential equation, you can do a comparison. But in this case, my qx equals to 2 over x. And my fx equals to x. So my integration factor u, which is the exponential to the integral of qx dx, would be equals to exponential to the integral of 2 over x dx. Okay, so you should be able to solve this integral very quickly, and we are going to get exponential to the log x. Okay, so noticing that the exponential and the log can be cancelled, so x simply equals, so my u simply equals to x in this case. And do not forget about the 2, so it's actually 2 here, and that will give me x squared for the u, the integrating factor. Again, the strategy is multiply the integration factor to every single term in the equation, which will give me x squared times dy dx plus x squared times 2xy equals to x squared times x. For the left-hand side of the equation, do not worry about simplifying it, because the whole term should give us the du, which is x squared times y over dx. And on the other side of the equation, we got x cubed. This is the portion you can simplify and do any organization. Okay, so if I move the x to the other side of the equation, I can do the integral. So on the left-hand side, I got the x squared times y. On the other side, I got x cubed times dx. I go ahead and do integral. After I do the integral, I got x squared times y on the left-hand side of the solution. On the other side of the solution, I can actually got the it should be x squared. Sorry, I missed the square here, which should be fourth term here. Okay, let me do the correction. Okay, and on the right hand side, we are doing the integral of x to the fourth power, which should be x to the fifth power over 5 plus c. Okay, all we want is y in terms of x, so we can divide both sides by x squared, which will give me x cubed over 5 plus c over x squared. Okay, so this is the solution I get for my y in terms of x. One thing you can actually do for the solution of y, you can bring the solution back to the initial first differential equation and try to see that the solution will make you have the same term on both sides of the solution. Okay? Okay, so that's for the first problem. And now let's look at the second problem in the practice, which is very similar but slightly different. Okay, so now let's look at the second question together. And again, we use the same strategy. We are trying to change and do some arrangement of the original function to look the same as the generic form. So in order to get the generic form, we divide every term by x, which will give me 1 over x times y for the second term. On the right hand side of the equation, I got 1. Okay, so now you can go ahead and do the comparison. So in this case, my qx actually equals to negative 1 over x. Do not forget about the negative sign. And my fx equals to 1. And the integration factor u, which is the exponential, and the exponent is integral qx dx, which will be exponential doing the integral of 1 over x dx. Okay, so this integral you should be quite familiar with. And we are going to get, do not forget about the negative sign here. You are going to get e to the negative log x. This is also equivalent to exponential log 1 over x, okay, which will give me 1 over x, because the log and exponential, they can cancel, which gives me 1 over x as my integration factor u. Same strategy applied again. We multiply 1 over x to the both sides of the equation, which should be dy over dx minus 1 over x times 1 over x times y. And on the other side of the equation, I just got 1 over x because it's 1 over x multiplied by 1. Okay, so for the left-hand side of the solution, it simply is du times y dx. On the other side of the equation is 1 over x. Then we can move the dx to the other side, which allows me to do integration. So I get d 1 over x times y equals to 1 over x dx. Okay, so now we can do integration on both sides, and this 1 over x times y comes out. And on the other side of the equation, I do integral of 1 over x, which should be log x plus c. And then I can multiply x to the other side and leaving only y as the left-hand side of the solution, which is y equals to x times log x plus cx. Okay, so different from the first question, in addition to the equation itself, one more condition is I know when x equals to 1, y equals to 3. How about we plug that number in? Y equals to 3 when x equals to 1, 1 times log 1 plus c. From there, you can find out c equals to 3. Okay? Now we can plug in the value of c to the solution, which will give me y equals to x times log x plus 3x. Okay, so this should be the complete solution for this problem. Okay, and so far we have pretty good practice regarding solving the first order differential equation. And moving forward, let's try to talk about what is the generic solution for second order differential equation. Okay, so the second topic we are going to discuss today is how to solve second order differential equation. The special case we are going to consider is a second order differential equation with constant coefficients. Okay, one example about the form of the function is the y squared over the x squared plus a times the first order differential dy over dx plus b times the y term. On the other side of the reaction, you can have fx. Okay, looks very familiar and is very identical to the first order differential equation, except we now get an additional term, which is the second order differential. Okay, to get started, usually we consider the reduced form like we do for the first order. So the reduced form are going to set fx equals to 0, which give me dy squared over dx squared plus a times dy dx plus b times y equal to 0. Okay, so the problem is how can we solve this second order differential equation? One strategy is people trying to guess what is a good solution for that. And one trivial solution for that, you can actually see if my y equal to 0, then no matter how many orders of differential I'm conducting, it will give me 0 for every single term on the left-hand side, and the right-hand side give me 0 for sure. Y equal to 0 is a solution for this equation. But how about non-trivial solution? Okay, can we take a guess? And one guess people take that works pretty good is I assume y equals to exponential to the mx. What is the value of m? That's something we need to figure out. Okay, so how about we plug in y equals to exponential to the mx back into the original solution. Let's see. So dy over dx should be m times exponential mx, right? So this is the differential we have done many times in the previous lecture. If I'm doing the second differential, I'm getting m squared times e mx. Okay, so I can plug these two terms back into the original solution, which give me m squared times e mx plus a times m e mx plus b times e mx equal to 0. We can factor out the e mx, and we got m squared plus a m plus b, the whole thing equals to 0. Okay, to find out the solution of this equation, if e mx is non-zero, then we have m squared plus am plus b equals to 0. See, now we transform the differential equation into a quadratic equation, which is easy to solve. You can just use the formula for the root. So m should be equals to, denominator we have 2, numerator we have minus a plus minus square root of a squared minus 4b. Okay, so this is my root for this quadratic equation. But what is the value for m is going to affect the final solution for the differential equation, and from there we are going to discuss the possibility of m. Okay, so first of all, if m is real roots, so all the roots are real numbers. Okay, and then the solution for y would be equals to c1 times e. So if the real roots is plus, and so let's see, if m equals to plus and minus a, then the final solution is going to be c1 times exponential ax plus c2 times e minus ax. This is the scenario when a are real numbers, which are the roots for m. Okay, so that will be my solution. The second scenario is when the m are imaginary numbers. Where m equals 2 plus minus ib, then my solution y equals to c1 times e plus ibx plus c2 times e minus ibx. This is the second scenario. The third one is my roots are complex numbers. Okay, so in that case, my roots will be equals to a plus minus ib. Okay, then the solution would be y equals to c1 times e, a plus ib x plus c2 times e, a minus ib x. You can reorganize the term by pulling the e ax in front of the other terms, and then you got C1 times E IB x plus C2 times E minus IB x. Okay, so this is the third scenario. The last one is when we have double roots. When m is double roots, meaning both numbers are exactly the same. In this case, the solution y is slightly different. We are getting C1 times E ax plus x times C2 e to the ax. So the formatting of the solution is slightly different compared to the previous three scenarios. Okay, so before we finish today's lecture, let's do one more example to review this part. Okay, so the question we are trying to solve . Okay, let's look at the second order derivative. Okay, so dy squared over dx squared minus 4 times dy over dx plus 4y equals to 0. Okay, so you can pause the video and work on the problem for 5 minutes. Then we come back and check it out together. Okay, so now you have finished working out the problem, and let's look at the solution together. So the auxiliary function for this one should be m squared minus 4m plus 4 equals to 0. To solve this quadratic equation, we can find out m equals to 2, which we have the fourth scenario. We have the double roots. Then the solution for this equation is going to be C1 times E to x plus x times C2 E to x. Or you can write it as C1 E to x plus C2 x times E to x. Okay, so we can have more practice after class. So to summarize what we have done today, we are trying to learn how to solve first order differential equation and learn some fundamentals about solving the second order differential equation. So in the first order differential equation scenario, we learned about the reduced form and the non-reduced form, and the integration factor u is the key to solve that type of equation. And in terms of the second order differential equation, we try to find out the solution for the reduced form first of all. To find out the non-trivial solution, we set the possible solution of y equals to exponential mx, and then lead us to the auxiliary function . From where we can solve the value for m for the quadratic auxiliary equation, there will be 4 different scenarios for the solution of m, which is real number, imaginary number, complex number, and double roots. Then the solution for y would be a linear combination for this exponential function, depending on which type of solution you find for m value by solving the auxiliary equation. So, okay, so that'll be for today's class. Thank you.